let's move on to continuous random variable models. So for this, we are going to talk about three different models: Gaussian, gamma, and exponential, but we will mostly focus on Gaussian distribution.
Before we get started, there's a hidden member.
So this is a uniform distribution. Uniform distribution is very simple. So, well, actually, uniform distribution, there is two different versions. One is discrete, and let us focus on the continuous version. So, continuous version of uniform distribution, parameterized by two real numbers, a and b. And a and b basically defines the range. So, within a and b, the probability is fixed quantity. So, the probability is fixed value, 1 over b minus a, always. And otherwise, you're going to have zero probability. So, where within this fixed region, you have some probability quantity, and that is shown in terms of CDF, so cumulative density function, where basically linear line. So, uniform distribution is very simple, but oftentimes you will see the name of uniform distribution in lots of text. So, well, that's why I try to add this up. So if you heard of uniform distribution, where you have fixed amount of probability over entire your probability ranges. Let's move on to Gaussian distribution. So Gaussian distribution, also called as a normal distribution. This is quite common, so we are going to talk about that aspect as well soon, but let's focus on how it is parameterized. So Gaussian distribution, random variable x is drawn from normal distribution, Gaussian distribution, and this is parameterized by mu, that means mean, and sigma, that is variance, sigma square actually. Given that, the probability value at certain point is calculated using this notation. And what it defines is depending on mu and sigma square value. So basically, it is defining a bell-shaped curve. So that is represented here. And the cumulative density function for each of these PDFs are given on your right as well. Here comes some geometric property. So it is centered around the mean value. So if you look at the parameter value here, so the blue curve and red curve and yellow one, where they are all centered around the 0. And notice that this 0 value happens to be the same as the mean value. And the sigma square is defining the shape or dispersiveness of the curve. So if the sigma value is large, where your distribution is wider, and if your sigma value is small, where things are peaked and narrow compared to the other ones. If you look at the green curve over here, the parameter value mean is -2. Again, this green curve is centered around the -2. And its sigma square value is 0.5. So it is where the width of this guy is somewhere between the blue one and red one. Well, since we know the PDF value, so where if you take the product of it and take the log in front of it, then it's going to be log likelihood. And what we want to do to estimate the parameter is to take the derivative and set it to 0. So if you do so, you can easily come to this notation. So mu, it means estimated. So the estimated mu is based on the data value. So basically, you're taking the mean value. And sigma value, well, initially you can try to come up with this by simply taking the maximum likelihood estimation. But well, estimator for the sigma value here is actually biased. So well, in your homework, one of the questions that you are asked is what is the meaning of biased and unbiased? And given this context, the Gaussian distribution, the biased estimator can be unbiased by taking some additional trait that is given over here. So well, this is somewhat related to your homework assignment. let's move on to some properties of it. Well, first of all, in terms of notation, it has two parameters, so mean and variance. So it is really easy to interpret if you know the parameter values. So it is centered around the mean, and variance means the dispersiveness. So it's straightforward. And Gaussian distribution teach many natural phenomena like age distribution, height distribution, or IQ score, or summation of some events, things like that. And there is a particular reason why lots of different types of events actually converging into Gaussian distribution. So theoretically, there is a theorem called central limit theorem. We are going to discuss it in a minute. But where as an effect, as an influence, Gaussian distribution is everywhere because a data set with finite variance turn into Gaussian. So where this part is again explained by central limit theorem. And although the notation here looks a little hairy, but it is still quite straightforward and it is not really complicated. Where especially if you want to calculate this using Python or any kind of language, where it is not really difficult to implement, where you can actually implement it in a minute. So where arguably Gaussian distribution is most widely used in statistics and machine learning. So it is important. And at the same time, let's try to explain why this is used so much in our real life. And many of the natural events, they are converging into Gaussian distribution. So this theorem over here, central limit theorem, is explaining the reason why lots of different events can be seen as a Gaussian distribution. So central limit theorem is stating is the sample mean will be approximately normally distributed. So if you collect set of data and take the mean, set of data, take the mean, set of data, take the mean, and you're going to have distribution of those mean values, where that distribution always approximately converging to normal distribution. So that is what central limit theorem is saying. Well, easily put, distribution of the sample mean tends towards the normal distribution as the sample size increases. So there is one condition, sample size should be large enough. But interestingly, the theorem does not state how large is actually large. The theorem is stating only the sample size should be large enough. The definition of large could be different from person to person. But noticing that central limit theorem has been defined more than 100 years ago. So given that, whereas the sample size was not that large from our consideration, and from the experience, general rule of thumb is the sample size is larger than 30. So everything is converging into Gaussian. That gives us lots of shortcut in terms of collecting data and analyzing the data and making inferences as well. That is kind of an additional explanation about Gaussian distribution. And let's move on to multivariate Gaussian. So previously, we are looking at a Gaussian distribution where x is scalar. So this is a single variable. But now let's consider where this could be a vector. So multivariate Gaussian distribution is looking at this random variable is a vector. So when x is scalar, we call that univariate, and x is a vector, we call that is multivariate. And this multivariate Gaussian distribution is again parameterized using a mean value and covariance matrix. And this mean is indeed a vector. And the PDF of Gaussian multivariate Gaussian distribution is given like this. So it has some coefficient in front of it, an exponent, and the difference between observation and mean, difference between observation and mean, normalized by covariance matrix. And if you visualize this Gaussian distribution, multivariate Gaussian distribution, it is defining the relationship between, well, the distribution between two different variables. So this is a two-dimensional Gaussian distribution. and still this is looking like a bell shape in multi-dimension. And if you look at the distribution of the data points from the top, then it will be like this. So it looks like an ellipsoid in the data region. So here are some additional derivation and some kind of a summation for log likelihood and maximum likelihood estimation. And also the same discussion applies to here. So where this is a biased estimate of a covariance matrix. And in order to make that unbiased, we want to divide it by n-1. And here are some additional properties of multivariate Gaussian. There is a theorem called the Cramer's theorem. So if a random variable x is following normal distribution, and say there is another distribution whose addition is forming x, given that x1 and x2 also normally distributed. So summation of two normal distribution is again normal. So this is a short summary of Cramer's theorem. Well, another property of Gaussian multivariate Gaussian distribution, well, since we are playing with multiple variables, so say x consists of x1, xa, and xb. Well, given that marginal distribution xa, so we are removing xb by taking the summation of it. So probability of xa is equivalent to taking the integral of the joint distribution xa and xb, and again the marginal distribution xa that is following a normal distribution. So this is another interesting and important property of multivariate Gaussian. So taking marginal of multivariate Gaussian is again Gaussian. The same property applies to conditional distribution as well. So probability of xa given xb. So you're conditioning xa on xb. The derivation is quite heavy here, so you don't need to understand this. But if you're interested, you're welcome to do that. But still, the important part is here. So the conditional distribution of xa given xb, that is again Gaussian distribution. The conditioning part can be understood as in this diagram. So you're conditioning something. So here you have joint distribution of probability y1 and y2. You're conditioning something given y1, certain value of y1. That is same as you're drawing a cut in this distribution. And you're looking at the surface after cut that is forming another Gaussian. So y1 is given as 1.6. Now you're looking at the distribution of y2 that is forming Gaussian. Well, here, same, you made a cut on y equal 1.0. So y1 is set to 1.0, and then the distribution of y2 is forming another Gaussian. So whatever you do on top of Gaussian, well, you are still ending up with Gaussian distribution. So you keep playing with Gaussian and exploring lots of techniques that built on top of Gaussian distribution. So that was univariate Gaussian distribution and also multivariate Gaussian distribution. And let's quickly take a look at gamma distribution. So gamma distribution, where the shape is, well, someone looks like this. So it has a sort of high peak, then goes down. And the peak is usually towards 0. So if your data looks like this kind of curve, then that's the time when you pull out gamma distribution and try to fit your data to it. So PDF of gamma distribution is given as this. Here, well, this gamma is actually gamma function representing the factorial. Other than that, well, if you take a look at the notation, you can understand it. Well, gamma distribution appears a lot when you study machine learning more seriously. So I'm not sure we are going to face this gamma distribution within this semester in our course. But if you take any higher level of course, And if you study where something like where LDA, latent deletion allocation or something, so some of the more up-to-date techniques where gamma distribution is occurring a lot in many contexts. On the other hand, exponential distribution is rather important. So exponential distribution looks like this. So it is different from gamma, where the peak was actually up from zero. So gamma was like this. But this guy does not have such a increasing part. So it is continuously decreasing from zero. And also defined from zero to infinity. So it is continuously decreasing from zero. And it has a single parameter that is lambda. So depending on the lambda value, where you're controlling the shape of the exponential distribution.